Okay, so good morning. Okay, so let's get started with today's one. Okay, so today's class is on the exceptions and interrupts. Again, nothing very new. Okay, we are familiar with the concept of exception and interrupt. Okay, but we are going to go deeper into how we implement this on the ARM processor. Okay, so as before, the poll is still active. All right, so anytime you need to ask a question, okay, so if you have any question, you can just put in the poll link, all right, and I will answer along the way. Okay, so what are exceptions and interrupts? Okay, so before we that, just a quick reminder on the assignment project team allocation. Just make sure that by this week, okay, if you are still without a team, okay, make sure you have already talked to your TA in the lab, okay, and they have allocated you to a team or group you all together. Okay, it's important that you are registered in Canvas, okay, as part of a team, because all the grading will be done through Canvas. Okay, so whichever team you register to, okay, all the grading will be done through there. Okay, so it's important that you are registered in Canvas. Okay, so just make sure your name is there together with your teammates. Okay, so we're going to go through exception and interrupts, all right, and understand how it is implemented on the ARM core. All right, and as always, have your data sheet on standby. All right, we'll always reference back the data sheet and learn how to extract the information from the data sheet so we know how to get what we want. Okay, so exception and interrupts. All right, so let's look at this simple example, okay, where we have a switch and LED. Okay, so this switch and LED, all right, as you can see down here, is connected. So by the default value is what? Okay, the way the switch is configured is the default value is pull to high, correct? Default value is pull to high. That means if I don't press the switch, okay, or the default value that I will read on the GPIO is a 1. Okay, and when I press the switch, I am actually creating a short circuit to ground. Okay, I'll create a short circuit to ground. Okay, and then when I release, it go back up. Okay, so it creates a sort of negative transition, okay, when I press the switch, okay, and then after that it goes back up again. Alright, as before, okay, as we have seen before in EBP2 and so on, okay, the mechanical switch is never so nice, correct? Whenever you press, okay, there is always a bounce before it stabilizes. Okay, which means there will always be a lot of what we call force trigger, okay, that is generated when you press the switch. Okay, and if you recall what we did before in EBP2, okay, we have like one of the solutions we implement is a timer delay, correct? A timer interrupt delay, where we say that the moment I first get the interrupt, I start a timer and wait for some time, correct? Before I continue, so I do not keep entertaining all this false trigger because of the bounce. Okay, so there are of course many ways you can handle it, alright, but it's up to you how you want to handle it. Okay, so just a quick question. Can I design my switch? Okay, let's say you are lazy. You say, why must put a resistor? Why don't I just connect the switch like this? Okay, so if this is my input pin, okay, this is 5 volt. So by default, it is high. When I close, it goes to what? Can I do something like this? Okay, so when you do something like this, what will happen? You will burn, you will see some smoke coming out, correct? Okay, why? Because you have created a short circuit directly between VCC and ground when you close the switch. Okay, so when you close the switch, you directly connect VCC and ground, means you short circuit. And usually what happens is when there is a short circuit detected by the board. Okay, most board will happen is they will actually go to a power down state or they will reset. Okay, so it's important that you connect your hardware correctly and you don't accidentally create a short circuit. Okay, same thing for your LEDs. So if I don't put a resistor, of course, very nice, very bright. Okay, nice to take video and put on TikTok. Okay, but then what happens? After a while, the whole LED will burn. Alright, so it's important why we do certain things. So even though LED is limiting the current, it is there to protect the LED. Okay, so the polling and interrupt method we are familiar with. Okay, so polling means we keep on checking whether a pin is or any hardware event has happened. Okay, but it's of course a very wasteful way of doing things because you waste CPU time in a very meaningless way. Alright, and a more efficient way would be to use the interrupt, okay, where you have the hardware in the controller to help you detect the event and trigger you when something happens. Okay, so the part is it is very efficient because you execute the code only when when the event happens. Okay, so what are the things that have to be handled when the interrupt or exception occurs? Alright, so we do not know when this event will happen, which means that I am actually running some code in the background, okay, your loop or whatever things that you are running, okay, and when the event happens, so it could be a push button interrupt, a ADC interrupt, a timer interrupt. When the event happens, I need to do certain things. Okay, the first thing is I want to do what we call the hardwired. Okay, why we say hardwired? Because it is designed in the processor itself, okay, to take care of all these activities. You don't need to write any code to do it. Okay, and what is that? That is basically the saving of your context. Okay, so what is the saving of the context? That means when I'm running, I need to keep track of where I'm executing the code. I need to keep track of my register, my data, my variables, everything. So I need to save all of that, okay, onto the stack that I'm using. Okay, again, this is handled automatically by the processor. And after that, I jump to the ISR. Okay, when I jump to the ISR, I finish the ISR. When I finish, I return back. So when I return back, I, of course, need to go back to where I left off. Right? I was somewhere here, correct? I was somewhere here doing something. So I need to be able to go back to the exact location with all the data that I was doing. Okay, so that is the restore portion of it. Okay, so when you say restore means what? We need to take back whatever that we save, put it back into the appropriate registers, and then I continue from where I left off. Okay, so this save and restore are what we call the hardwired activities. Okay, exactly what are the registers, how I use the stack, all of this is again when you learn the assembly language part, okay, in your other module, then you will look at this. Okay, your program counter, your stack register, your link register, and all the other registers you're using, which stack I use, how I use the stack, all of this is sort of the assembly language part. Okay, so, but in our case, we just understand the save and restore context. Okay, so again, why we want to use interrupt is because they are the most efficient way of handling asynchronous events, okay, and I can have a separate code that will execute as and when the event happens. Alright, and again, it actually is a way of multitasking, correct? The interrupt mechanism we have actually allows multitasking, okay, even without an OS, okay, but again, we are limited. Okay, so yeah, so this actually allows multitasking, alright, but it's just that it's currently without an operating system relying on the interrupts. Okay, so this is a general idea, okay, but we will not worry about this. Later when we look at the actual lab that they're supposed to do next week, we will understand this better. Okay, so the basic idea is I have a switch that will trigger an ISR, and in the ISR, I will be able to control the behavior of my RGB LED. Okay, so this is the objective for the lab, which we will look at later. Okay, so let's look at the actual interrupt mechanism within the Cortex M0 Plus that we are using. Okay, so in terms of interrupts, again, we have what we call hardware interrupts and exceptions. Okay, the hardware interrupts are asynchronous, like your timer, your ADC, your push button, and so on, because we do not know exactly when it will happen. You also have what we call software interrupts. Okay, that means you can actually trigger an interrupt, okay, when certain things happen in software. For example, an undefined instruction, okay, some stack overflow, and so on. Okay, so when there is some event in the software, you can also trigger an interrupt, or what you call an exception. Okay, and the ISR is the code that is tied to whichever event we are trying to capture. Okay, in the ARM processor, alright, all ARM processors have what we call this nested vectored interrupt controller. Okay, the NVIC in short. Okay, and this NVIC is the one that manages the interrupts coming in from all your peripherals. Okay, so this NVIC over here, okay, as you can see, manages all the interrupts from all your peripherals. Okay, whether it's your GPIO, your timer, your ADC, and so on, everything comes through the NVIC, and the NVIC is the one that sends the signal to the processor core over here. Alright, and here you can also see there is also a wake up interrupt controller. So what is this wake up interrupt controller? It is the ability for you to wake up your system if you put your system in some sleep mode. Okay, so if you remember, we can put a controller or a device into what we call a sleep or deep sleep mode, where it consumes very little power. Okay, then how do I wake up the device? So I need to send some wake up signal through the interrupt, and some of these peripherals will have this ability. Okay, like for example your printer, alright, if your printer you never use for very long, okay, it goes to a sort of sleep mode. Alright, the lights go off, you think it's off, but actually it's not off. Okay, the moment I send a print job, it can wake up and process the print job for me. Okay, the same thing. Okay, why? Because the serial interface or the USB interface that is taking this incoming data is programmed to wake up the device. Okay, so you can wake up the device and get it to process the information that is coming in. Okay, so the interrupt sources. Okay, what are all the interrupt sources? Okay, so the interrupt vector table, okay, has all these interrupt sources where you have a interrupt vector number, alright, tied to some address. Okay, tied to some address, and that also ties to a IRQ number. Okay, so these are just some of the vector table entries. We will look at the whole vector table entry. Okay, now what is a vector table? Okay, so let's look at this again over here. Okay, so if you look at this table in your data sheet, like I said, we will always go back to the data sheet so that you are more comfortable with looking at what is there. Alright, so in this vector table, okay, or interrupt vector table, you will see all the interrupts that are supported, okay, by the processor. Okay, now let's look at this. So you can see down here that address 0 is your initial stack pointer, address 4 initial program counter, and so on. And then these are all the, what you call the core vectors. Okay, the core vectors means they are fixed, okay, in terms of the priority. Okay, then you have all of this non-core vectors. Non-core vectors are vectors associated with all your peripheral subsystems. Okay, so in this case, for example, your DMA, your I2C, SPR, UART, timer, okay, and then you have your port A and port D as well. Okay, so all of this is tied to some address. Okay, it's tied to some address. Okay, so let's again recap how this whole thing works. Okay, so copy this. Okay, so in interrupt vector table, how does it work? Okay, so for example, let's look at the basic one, the reset. Okay, whenever I reset my device, how do I ensure that the system always boots up the same way? That means it must always go back to the same starting point, correct? Okay, there must always be a way for me to go back to the same starting point. Okay, and in every controller there is this thing called a reset interrupt vector. Okay, which means what? That means whenever I power on my device, I will always go to this same address and start executing my code. Okay, so the initial boot up code will always come to this address. Okay, this reset interrupt vector address. And what will I do? I will start executing the code. Alright, now the same concept applies to all your interrupts, okay, at this entry table here. Alright, so right now, okay, for example, I am now going to configure, let's say, port D interrupt. Okay, let's say I want to connect my switch to port D, okay, and I configure my interrupt. Okay, how to configure, we will see that in a while. So after I configure, okay, let's just say that I want to capture the positive edge on port D, okay, one of the pin on port D. Okay, and I have done all my configuration. Now after I have done all my configuration and everything is set, and I go and press this port D switch, okay, what will happen? Okay, what will happen is the interrupt that is configured will now send the information to the NVIC controller, correct? Because the NVIC controller is the one that handles all this peripheral interrupt requests coming in. Okay, so the NVIC, okay, based on which line is triggered, it will know that, okay, now port D has triggered me, correct? Okay, and it will relay that information to the Cortex M0, or the processor core. And what will the processor do? Okay, since it has received an interrupt, okay, what must it do? It must, okay, initially it was in the main loop, okay, doing something, correct? And now the push button has come in, correct? The interrupt has been triggered. So what I need to do? I need to first do the hardwired activity, correct? Which is the saving the context. Okay, so from here I will first save the context. Okay, I will save my context when the event happens. Now after I save the context, I need to now jump to the ISR, correct? Okay, how do I jump to the ISR? Okay, so to jump to the ISR, I need to do two things. Okay, firstly, I need to know where is my ISR. Okay, your ISR is a code that you write, correct? So somewhere in your code, okay, you have a port D ISR. Okay, some code that you have written. Okay, so the exact syntax, we will look at it later, but just take it that I have written this code, the ISR code that is supposed to be executed when the switch button on the port D pin is pressed. When I compile my whole code, what happens? My compiler will place this code somewhere in memory, correct? We do not know where it is, but it will be somewhere in memory. So we know that right now, this code, when I compile, it has come to some place in memory, correct? Okay, it can change anytime, every time I compile, doesn't matter. Okay, so let's give it an address. So let's say I give this as an address A000, just a simple 16-bit address. Okay, so I'm giving this address to the code where the ISR is stored in memory. Okay, now I need to execute this code, correct? When the push button is pressed. So when I compile my code, okay, at the same time, what will happen is this address, okay, this address will also be copied, okay, and put in the vector address location. That means 000BC. So the address A000 will come here. Okay, the address A000 will also come to the entry of the interrupt vector table. So there's two parts, correct? One is the ISR, the actual code, which will be anywhere in memory, and the location of where that is in memory will be stored in the actual interrupt vector table. Okay, so when the event happens, okay, after I save my context, after I do this, okay, in order for me to jump to the actual ISR, I first come here. I come to the vector table entry. I come to the vector table entry here. I take this address and I put it into my program counter. Okay, a program counter is a register that tells me the address of where I should execute. Okay, and since I have the value of A000 inside here, I will now point to this location and I will start executing. Alright, so when I finish everything, when I return, I want to restore the context. Correct? When I finish everything and I want to return, I must be able to restore the context. And to do that, I will now load back whatever that I saved before and continue from where I left off, which is here. Okay, so this concept of interrupt processing is uniform. That means across all controllers, they have the same idea. Okay, I have a vector table which basically tells me where I will go to when the event happens, but in the vector table, I only have the address of where the code is stored. Okay, so I will first go to the vector table, take this information, then put it to my program counter and then execute the code. And then after I'm done, I will come back. Okay, so this is the whole idea of the how interrupts are handled in general. Okay, so this is again something that you just need to be comfortable with because all controllers have the same mechanism. Okay, so just now we talk about priority. Okay, we talk about priority. So the core vectors are all fixed in priority. The first 16 are all fixed in priority. Subsequently, the non-core vectors, you can allocate your own priority using what you call the IPR registers. Okay, so there are a total of 8 IPR registers over here. And for each of these registers, you can see that even though it's 32 bits, I break it up into chunks of 8 bits. Okay, and even in the chunk of 8 bits, I only use the upper 2 bits of each 8-bit block. Okay, so to give you an example, okay, if I wanted to update the priority of IRQ18, okay, if I wanted to update the priority of IRQ18, I need to come to the IPR4 register and I need to update the bits 23 and 22. Okay, now of course, it looks very troublesome, correct? I need to know which register, which bit, and so on. So to make our life easier, there is actually a built-in API we can use, which is what we call the NVIC set priority. Okay, so I just use this. Okay, later you will see in the code how it is used. I just need to use this, provide the IRQ number. Okay, the IRQ number that I am currently trying to set, and put the priority level. Okay, so the priority levels are 0, 1, 2, and 3. Okay, 0 is being the highest priority, and this is the lowest priority. Okay, so 0, 1, 2, and 3 translates to 0, 64, 128, and 192. Okay, why these funny numbers? Because it comes down to the only upper 2 bits being used. Correct? The rest are all zeros. Okay, so if 0, 0 is 0, 0, 1, 64, 1, 0, 128, and 1, 1 is 192. Okay, so if you look at it as an 8-bit value, where only the upper 2 bits are changing, then the 0, 1, 2, 3 translates to these 4 numbers. Okay, so that's how you relate 0, 1, 2, 3 to 64, 128, and 192. Okay, so later in the code, we will see how these calls are all made. Okay, to enable interrupt, I use this function, NVIC enable IRQ. If I want to disable, I say disable IRQ. Okay, so we will again look at that later. Okay, this set pending IRQ allows us to set an IRQ in code, okay, without a hardware trigger, or if a IRQ has been registered but not yet serviced, I can also clear it. Okay, so in the case, for example, I am having nested interrupts, and while in the current interrupt, another interrupt happens, and I don't want to handle it, I can clear it. Okay, so it allows me to clear a pending IRQ, okay, without servicing it. Okay, as a global mask, okay, as a global mask to enable and disable interrupts, there is a prime mask exception register. Again, it's actually assembly language code, but we are given two library functions which you can use. Okay, enable IRQ and disable IRQ if I want to have a global enable and disable of interrupts. Okay, again, priority, I think we have seen just now. Okay, so all the core interrupts have fixed priority. The peripherals have adjustable priority using the IPR registers. Okay, how about the case of the nested interrupts? Okay, so in the case of nested interrupts, what happens? Okay, if the new interrupt is, or new exception is higher priority, then I will actually preempt my current interrupt. Okay, so for example, if I have my main loop running, okay, and I have port D interrupt, and I have port A interrupt. Okay, and I say port D is priority level 3, and this is priority level 1. Okay, so if, while I'm in my main loop, if port D triggers, I will jump to port D interrupt first. Okay, and before I finish, if port A triggers, I will jump to port A. Okay, so by default, the processor allows nested interrupts, which means as long as the higher priority interrupt is triggered, I will jump there. Okay, but what if the other priority is equal or lower? Okay, if it's equal or lower, then I will still register it, but it will be what we call a pending state. That means the processor knows that the interrupt has been triggered. Okay, but I will finish what I'm doing first, and then I will jump. Okay, so it handles both cases, whether it's higher priority or equal and lower. Okay, so coming back to our example, all right. So the KL25Z GPIO again has all these ports, all right, but only port A and port D support the interrupts. Okay, so as you saw from the interrupt vector table, only the port A and port D are mapped to interrupts. Okay, so in terms of the connections, okay, we only have some of these pins that are available for interrupts. Okay, the port A pins and the port D pins. Okay, so for the hardware, okay, that you're going to set up for the lab, okay, we're going to connect a switch. Okay, we're going to connect a switch to the port D pin 6. Okay, so port D pin 6 is going to be connected to a switch. Okay, and if you look at this configuration, what is this configuration? So if I draw the circuit here, I have a switch here and connected to ground. Correct? That is how the circuit is connected up. Does this look correct to you? If I press the switch, what happens? It goes to ground, correct? That one is clear. But if I don't press the switch, then what is the voltage I will read? If I don't press, what will I read? You don't know what you will read, correct? It's considered a floating pin. Okay, so you should never have a floating pin, correct? You should never have a floating pin, because if it's a floating pin, there is some electrostatic signals in the air, it just picks up, then it will trigger a false spike. Okay, so you should never have a floating pin, okay, but yet this is correct. Okay, why is this correct? We will look at it later. Okay, it is basically because your controller, which is also available in your UNO, you have your internal pull up and pull down. Okay, so even though I don't see any resistor, but internally I can actually do a pull up. Okay, so this is internal to the controller. I just activate with the register setting. Okay, so there is a pull-up resistor or a pull-down resistor that I can use that is internal, so I don't need to physically connect it, okay, on my board or the circuit. Okay, so now to do this, okay, to do this lab for next week. So this week's lab is just the GPIO driver, get familiarized with the board, okay, the RGB LED and so on. Now for next lab, you need to do this, which means what? Which means you need to solder the header pins. Okay, so even though we did soldering before, okay, I know many of you just gave a lot of eye power, correct, while your friend was doing all the soldering. Okay, which means some of you are very good, some of you haven't even touched the soldering iron yet, correct? Okay, so for this board, okay, since the board is very, very precious and we can't afford to damage it, okay, please don't use this for soldering practice. Okay, if you want to practice soldering, I can give you a lot of additional empty boards and wires and connectors you can practice. Whole day you can sit in the maker's lab and practice. Okay, but for this, don't do that. So whoever is the best in your team, or if not us, outsource to some other person in another team. Whoever is good, ask them to help you. Okay, because you need to make sure all this soldering is correct. Okay, and it's very neat and very nice. Okay, don't over solder, don't overflow, and everything short each other. Okay, that everything is chaotic. Okay, so be very careful, and also make sure when you solder, the chip is facing you. Okay, I have people who solder the other way. Okay, you cannot go wrong, please. There's only one way you can put the board. Okay, and the header pins must be facing you. Correct, the connectors must be facing you. Alright, so make sure that you get it correct and ask whoever is good in soldering in your team or in your lab to help you out. So this is important. Okay, so the code wise, okay, we will go through the code shortly, okay, with all the concepts of how to initialize your registers, how to put your ISR and so on. Okay, now before we do that, okay, we are going to quickly recap this important concept that we have to be very comfortable with, which is the volatile variable. You all remember this volatile keyword? Okay, EVP2, we talked about it a few times, but we need to understand it as well. Okay, so what is this volatile keyword and why is this very, very important in our embedded programming? Okay, when I normally write a code like this, integer x equals to 0, and I write a loop x equals to x plus 1, what happens? Okay, so when I compile my code, okay, I will set aside this some memory location to hold this variable x for me. Okay, and when I want to execute this code, what happens is at the assembly language model, okay, the ARM is basically what you call a load store architecture. A load store architecture, which means that what? Before I can do anything, I need to load. Load means I take the data from my memory, put it into my internal register, perform the computation, and then eventually I'll write back. Okay? So rightfully what happens is I will need to do a load operation from memory to my internal register. After I do that, I pass this to my ALU. Okay, then I say I want to add with a 1, correct? After add with a 1, then I must do a store. Okay, so every time I run this loop, by right I should do this. But memory access is always the slowest link in the whole thing, in the whole system. Okay, your processor is very fast, your memory access is very slow. Okay, like what they say in NS, rush to wait to rush. You know what I mean, correct? You do things very fast and then you just sit down there and you sleep. Nothing's happening, and then you rush again. Alright, the same concept. So you can process your computation very fast, but I read data very slowly, I write data very slowly. Okay, so to make life better, okay, or to speed up things, usually what your compiler does, okay, to optimize is, it doesn't do this all the time. It does it in the beginning and does it at the end. Okay, so if I'm going to run this loop, let's say 100 times, I only load the x value when I first want to before I run the loop. Okay, and then subsequently I just run the loop. When I finish the loop, then I do a store X. Okay, because it is still logically correct. The X value is still retained in my register. I still do the correct computation, but when I finish everything, then I write back. Okay, so this is how the compiler will normally optimize your code for you. Okay, to minimize access. Okay, so in order to so this is normally how it works, and it is fine in an environment. Okay, an environment where there is no alternative way of updating this memory location. Okay, but in the context of the interrupts, okay, if I have an interrupt here, okay, and inside the interrupt, I'm also updating X with some value. Okay, and this interrupt is, let's say, tied to the push button and so on. Alright, then what happens? This code is unaware that this other code is going to run, correct? Because this other code is not called as a normal function. Okay, it's not called as normal function. It can happen asynchronously at any time. So if I do this load X and store X, okay, before and after the loop, but while I'm running the loop, the interrupt happens, then this is not captured, okay, to update X. Okay, so this load and store will now mess up my overall sequence of values. Okay, so that is where this volatile keyword comes in. Okay, so if you have a variable that is shared between your main code and your interrupt, okay, what we want to do is we want to make sure that that variable is now declared as volatile. Now when I declare it as volatile, what happens? What happens is when the compiler compiles, okay, it will still do the same thing. It will now do a load. It will do whatever I need to do, and then it will do a store. Okay, and since it is volatile, it will do this every time. Okay, which means that even if in the midst of the loop, the interrupt is triggered, I will still get the updated value. Correct? Because the ISR will now update the value to the memory, and the loop will still get the latest value from the memory. Okay, so sometimes, okay, you will see that, I never use volatile, it still works. How come? Okay, again, it depends on how the code is written, how the code is optimized. Okay, so in some cases, you may say that I never use volatile, it still works, means it is happen to be the case. Okay, because of maybe the code structure and what you're doing with the variable. But it's always good practice to put volatile keyword if there is a shared variable between the interrupt and the main code. Okay, so that is again a recap of the volatile. Okay, all of this I will cover. Okay, this part on how to set up everything, we'll look at it later when we go through the whole code. Okay, now I will look at the registers. There are two registers that we need to configure. So the registers that we used before are still the same. Okay, your power control, which register is that? If I want to on power to any of the port, which is the register? You remember? S, start with S. SCGC, remember? SCGC, there is a few SCGC registers. So power to the port is SCGC 5. So I need to enable power first to the port. Always remember, you need to enable power before you do anything else. Okay, so always enable power, and after you enable the power, then you configure the registers. So last week, we actually looked at the PCR register. Okay, the pin control register to configure the mark setting. Remember, the mark setting is to select which function that I want. Is it GPIO function? Is it some other alternate function, and so on? Okay, so that is one of the uses of the PCR register. Now we will look at another use of the PCR register, which is the IRQ setting. Okay, so the PCR register, there is one PCR register for every pin in the port. Okay, so every pin is individually configurable. Okay, it's not a global setting, it's individual setting. Okay, so for the PCR register, bits 16 to 19 are used for the IRQ configuration. Okay, so if I want to interrupt on rising edge or falling edge, okay, depending on what I want, I need to configure these bits. Okay, how to configure these bits? They are already built-in macro functions in the header file which we will use. Alright, so we don't need to directly go to each register and find out which bits. We can use the built-in macro functions and they will help us to set these bits for us. Okay, which we will look at in the code. Okay, so okay, let's come to the code later. So later I'll come to the code and the demo part later. Okay, so some other stuff about ISR before we go to that direction. Alright, so interrupt service routine, again some important things you must know. There are no arguments and no returns. Alright, so there's no way you can pass argument to ISR and there's no way you can get a return value. Of course, one of the way you can do it is what you like to do always, right? Global variable. Alright, I'm sure your code has 2000 global variables by the time you finish. Okay, but of course it is not a good practice. Don't put everything as global and say solve all my problem. No need to send, no need to receive. Everybody can access everything. Okay, so it is global variable is like a double-edged sword, correct? It can make a life very easy, it can make a life very miserable. Okay, why? Because if somebody else mess up your variable and then you do not know, correct? Okay, and then you go and use a variable. Alright, so there are certain things that we must learn how to make our code better. Again, keep it short and simple. Okay, don't write a 2000 line ISR. Okay, ISR is supposed to be very short and simple. Do what is really important and then we sort of offload the rest later on. Okay, how to label the IRQ handler all. Okay, we look at it based on the header file and all the macros we have. Okay, and once I'm inside the ISR, okay, I need to do two things. I need to clear pending interrupt and I also need to clear the interrupt status flag register. Okay, this is to tell the processor that I've already serviced the interrupt. Okay, so if you remember, the NVIC tells the processor, correct? The NVIC tells the processor that there's an interrupt. So when I finish, I need to update the status flag to tell the NVIC that it's already done. Okay, so I already finished what I'm supposed to do for the interrupt. Okay, so how do I do that? I need to do two things. Alright, first I clear the pending interrupt. So when I write my port handler, so in this case port D IRQ handler, okay, what I need to do is first I clear pending IRQ. Okay, clear pending IRQ means I will clear, I'm telling it to clear any interrupt. Okay, now rightfully, okay, this is legacy code. That means even if I remove this code, it still works. If I remove this line of code, okay, but this is again legacy code. Legacy code means what was originally practiced, okay, but now architecture has changed a bit, so without this it still works. Okay, but it is again still in most literature, so I just put it here. So even without this it will still work. Okay, but it's still there to clear pending IRQ. Okay, next is I want to check the port D ISFR and with a mask. Okay, so what is port D ISFR and mask switch position? Okay, this ISFR flag, okay, is a status flag register that is tied to each of the port that tells me whether each particular pin is triggered or not. Okay, so let me show you over here. Okay, so you can see that each port has its own ISFR. Okay, so this is port A, say port B, port C, port D. Okay, so let's say I go to port D1. Okay, so what do you see? You see 32 bits register, correct? This ISFR is 32-bit register for each port, and what it tells me is I'm able to check which particular line triggered. Okay, so if I have multiple switches on different port D pins, for example, I will able to clear individual interrupt. Okay, and I will also be able to check whether which interrupt is the one that triggered the event. Okay, so once I know that particular event has happened, I must come to this register to clear the interrupt. Okay, this ISFR register to clear the interrupt. Okay, so again we will go through all this later when we're looking at the demo. Okay, so timing analysis, again just to give you the idea of how things look like. Alright, so in this case we are looking at a switch. Okay, when the switch is triggered, okay, in this example, when the switch is triggered, then there is a there's an ISR here. Okay, so this is the ISR. Now if you look at this timing, okay, basically what we are trying to show you is your ISR timing is very, very short compared to the rest of the code. Okay, why? Because your main loop, okay, your main loop has some periodic activity that keeps on going. Okay, and if your ISR takes too long, okay, ISR takes too long, then what happens is you will find that by the time you come back to the main, a lot of time would have passed. Okay, so the whole idea is you want to keep it as short as possible, okay, so that you can go back to the main quickly. Okay, now this interrupt response latency, we have talked about it, is about the saving context, restoring the context and going back, and of course how much time you take. Okay, now this concept of the CPU clock frequency, the interrupt timing, all this, I will leave it first. We will discuss this in the tutorial. Okay, so in next week's tutorial there will be some questions on this, then we will come back to this concept of how much time you will take in the clock frequency, the overheads and so on. Okay, program design with interrupts, I think we have done this before. Okay, I will not go through so much. Okay, sharing data, again like I said, for now we have global variables, okay, but we will have better mechanisms later on when the OS part comes in. Okay, so for now, yes, we still have global variable, but we will look at something better later on. Okay, so the midterm announcement. So I know you all have given me feedback. 16 March you have EE2211 assessment at 10 o'clock. Okay, so it's only two timing. Either I start at 8 o'clock or I start at 12 o'clock. I think 8 o'clock everybody's still sleeping. Okay, so the better timing will be at 12 to 1. Okay, on 16 March. Okay, so why I have to switch date is also because 9 March I didn't realize was also open house day. Okay, so also some of you give me feedback that some of you are involved, okay, in the open house. Alright, which means that the timing also is an issue. Alright, so I will send an announcement on this and also on the topics, okay, and the mode. Okay, the format will be MCQ. Now, format MCQ, the topics that are covered, how many questions, all of that I will update you all soon. Can? 16 March, 12 to 1. Okay, so you will have to split into two different LT. Okay, so one will be this and probably one other LT nearby. Okay, so don't worry, I will send an announcement on this so that everybody is aware of the plan. Okay, so before we go for a break, like I said, every time I'll give you some life hack. Okay, so today's life hack is interview question. Okay, so some of you may have gone for interview before already, correct? Maybe for internship, SCP, NOC and so on. Okay, usually when you go for a job interview, minimum 2 or 3 rounds. Okay, and the first and second round is usually what we call a technical interview or technical test. Okay, so in many cases it's a written test. Okay, it's a written test and sometimes there are a few candidates. Okay, sometimes it's only you. Okay, and after you do a written test, after the written test, they ask you to go back home, means that's it. Okay, but if they call you for the next round, means okay, then got chance. Okay, they got chance. Alright. So if you finish the technical test, correct, and they are happy with the technical test, they will call you for the next round interview. Okay, and the next round interview could have some technical questions. Okay, in the past, many companies like to ask funny questions. You know what I mean by funny questions? That means they ask you questions that are technical but not technical. Okay, so let me give you an example, and you think about this. So these are real life questions that have been floating around. This is a real life interview question. How many passenger cars are there in Singapore? So it's a technical question, but it's not a technical question. How will you answer this question? Huh? No. How do you answer? That means, if you are an interviewer and the interviewer asks you, how many passenger cars are there in Singapore? Do you know the answer? You don't know the answer, correct? I still don't know the answer. Okay? Chances are nobody knows the answer. Okay, unless you are looking at some data set from LTA in the past, then you know, correct? If not, there's a high chance you do not know the answer. And trust me, they're not interested in the answer. Okay? When they ask you this kind of funny question, they're not interested in the answer. But what are they interested in? They don't want you to give a final solution. They want you to reason out with them, how can I arrive at this final answer? Correct? That's what they're looking for. They're not looking for a final answer. They are looking at how you think through the question to arrive at some answer that can convince them. Because that's what engineers are supposed to do, correct? And you have a problem, and you're supposed to solve the problem, and you try to think of some way that I can solve the problem. Okay? So if let's say I've asked this question, okay, how will I answer? Okay, you may answer it differently, but what I'll answer is this, okay? I will say that, okay, I live in a HDB estate, okay, and in these few blocks there is a multi-story car park. So in the multi-story car park, I have 4 levels, each floor being 50 cars. So I got 200 cars in my immediate vicinity, correct? And let's say you live in Clementi. Okay, so you can say in Clementi there are maybe 20 such multi-story car park. So 20 times 100 or 200, correct? Then there are maybe 50 such estates in Singapore. Then I multiply. You know? So eventually maybe you get some answer, which could be totally off, but doesn't matter. Correct? Like I said, they're not interested in the solution. Correct? But as long as you can think through and give them some systematic way of how you're going to arrive at the final answer. Understand? Okay? So that is important, because in engineering, you cannot just say, I try my luck. Okay, why I put this resistor, why I put this delay, why I put this loop. You cannot just say, I try, it works, so I just stick to it. Okay? Many times we do that, correct? We have a problem, we just say, try a loop, try this, try that. It works means we're happy. Alright, but maybe it never solved the problem. Correct? Maybe it just masked the problem, but the problem is still there. Okay? So as long as you understand how to reason out with somebody, it's important. Okay? So that's also a reason why in most places they also have what you call code review, correct? You all have done code review before? Correct? What is code review? You ask somebody else to look at your code, correct? Somebody else to look at it. Okay? Many times, okay, from experience, when I'm stuck with the problem, I talk to somebody who doesn't know anything I'm talking about. Okay? So if you're stuck with a problem, you talk to somebody who has no idea what you're telling them. And why you do that? Because if that person has no idea what you're telling them, you're trying very hard to explain, correct? And when you try very hard to explain, then you realize that actually a lot of things you do not know. Correct? Then you realize all the things you know and you do not know, and then you go back and look at your own design. Okay? So try to talk to somebody who really doesn't know what you're talking about, and then that will give you a chance to go deeper into what you're trying to explain. Okay? Okay, so we'll go for a break now. Okay, after the break, when we come back, we will look through the code, we look through the demo, okay, and then the Kahoot. Okay, so now it's 11, we'll take almost 11 now. We'll take a 10 minutes break. Okay, at 11:10 we come back, then we'll do the rest. So far the poll is very quiet, this is the quietest. Okay, so let's look at the code for next week's lab. Okay, so one of the things you must also do for next week is you also need to solder the wires for the switch. Alright, so we haven't issued you the switch yet. Okay, so next week when you come to the lab, we'll issue you the switch. Alright, so make sure you solder the wires to the switch as well as the header pins. Okay, so let's look at review the code. How does the code looks like? Okay, so since we are using port D, okay, so I will not go through the GPIO code for the LED and so on. That is similar to what you already developed. Okay, so for the switch, what we need to do? We need to enable the power to the port D mask. Okay, so we need to enable the power to the port D because we are using port D pin 6. Using port D pin 6. Alright, now the PCR register. Okay, so let's look back at the PCR register. Okay, so this PCR register is an individual register for each pin. Okay, so every pin has its own PCR register for me to individually configure all these settings. Okay, so the mark setting, okay, so there are a few settings over here. Okay, so let's look at it one by one. So the first one is the port PCR marks. Okay, so the port PCR marks over here, what does it do? This is for the GPIO, right? The marks one is for the GPIO setting. Next is this two, PE and PS. What is PE and PS? Now what is PE and PS? If you look back here, this PE and PS is the one I talked about just now, which is the pull enable. Remember, the switch is floating, looks like it's floating, correct? Okay, but it's actually not floating because we enable the internal pull-up. Okay, we enable the internal pull-up, okay, for the pin, port D pin 6 pin. Okay, so that is why, okay, the port D pin 6 pin, okay, internally, okay, even though outside it just looks like this, okay, it looks like this, but internally we have connected it to a pull-up register. Okay, so that is the internal pull-up setting. Alright, then there's one more setting here for the IRQC. I have passed in a value of 0xa. Okay, so 0xa means, again, we can look back over here at the table. Okay, A is 1010, which is interrupt on falling edge. Okay, so I'm configuring the interrupt, okay, to be on the falling edge, 0xa. Alright, so again, you can see that we are using all these built-in macros. So where are all these macros? Okay, so if you look back at your the actual code, okay, when you load the code in your IDE, okay, you can always right-click, okay, and go to the definition of all of this. So if you go to the definition, you will see that, okay, the IRQC hex define, what does it do? Is they take the value that I provide, go shift left by shift amount and do the mask. The shift left is how much? The shift left here is 24 bits, correct? Okay, and then I do the mask. Okay, the mask is the 0x1000. Okay, now why do I shift left by 24 bits over here? Sorry, IRQC shift is here. So 16. Okay, IRQ shift is 16 and our mask is 11F0000. Okay, why? Because it ties in with my So it ties in with my status register setting here. So you can see the IRQC is 16 to 19, correct? That means whatever value that I pass in, okay, whatever value that I pass in over here will be shifted to the left by 16 bits. Correct? Based on the IRQC shift. Correct? I'll shift left 16 bits. Correct? And then I mask it with F0000. This F here is actually signifying what? It is actually signifying these 4 bits here, correct? 1111. Okay, so you can see that the built-in macros that they provide allow you to give a value, okay, depending on what setting you want, and the macro does the shifting and masking for you. Correct? That means it shifts this value to the correct bit position and does the masking so that you only update those bits. Okay, so it sort of helps us to make sure that using these macros, the correct value is updated to the correct bit position in the register. Okay, so when I do this, okay, and this is for the switch position. So for this particular bit, okay, which is bit 6, okay, on port D, I am now using GPIO function. I have enabled pull up, and I have set the thing to interrupt on falling edge. Alright. Okay, so these are all the settings I have done. Okay, then the DDR register is to set the direction to be input. Correct, because I'm now reading from the switch. Okay, next is this tree setting over here. This tree setting for the interrupt. Okay, so what are the things I need to do? I need to set the priority. Okay, so when I set the priority, okay, I need to specify the IRQ number here. Port D IRQN. So where is this port D IRQN? Okay, so if you go to a header file, okay, you scroll all the way to the top. Now all the way to the top, you will see the entire interrupt vector table in the sequence. Okay, it is exactly like what we saw just now in the data sheet. So all the device specific IRQ numbers are all here. Okay, and we are looking at port D IRQN. So actually what we are passing in is the number 31. Correct? Why 31? Because 31 is the one that is tied to the interrupt vector table entry. Okay, this table there is exactly the same. Okay, let me show you over here. Okay, so can you see that the numbers are exactly the same? IRQ number, the 30, 31, everything here is the same as the whatever you see on the table here, correct? This number here. Alright, so whatever that you see in the data sheet has already been mapped for us, okay, inside the header file. Alright, so when I am calling this code, okay, I'm actually interested in only the number 31. Alright, but again, if you put 31, we know what we're talking about, correct? So it's why in the header file, everything is nicely defined with the name. Okay, so the port D IRQN is actually interrupt vector 31. Okay, I'm setting it to a priority of 2. Okay, so in this case, the actual number here doesn't matter because there's only one interrupt. Okay, whether I put 0, 1, 2 or 3 doesn't matter, it will still be the same. Okay, then I clear pending IRQ and then I enable. So this tree is to make sure that the interrupt is set up correctly to capture the button event. Okay, now after I do all these 3 things, okay, then so of course I call the init switch inside my main function, okay, and then I have the IRQ handler. Okay, so this port D IRQ handler, okay, this port D IRQ handler is the name, okay, that I must use for each interrupt. So it depends on whichever is the peripheral name, okay, the underscore IRQ handler. That is the naming convention you must follow. Okay, so inside this, okay, IRQ handler, what is happening? Okay, so the first thing that I do is I clear pending IRQ. Okay, so to clear pending IRQ means since the interrupt has already been registered, I clear it first. Okay, but again this is legacy code. You can see later if I remove this, it will still work. That is fine. Okay, now the actual thing that I want to do in my code is this. Okay, I'm just doing two things. Okay, so this is not your exact lab thing, a lab that you're supposed to do. In your lab, you're supposed to toggle between the different LEDs. In the demo here, I'm just going to switch on and off the LED. Okay, it's just a single LED. Okay, so I'm going to do two things. I'm going to increment my count. Okay, there's a reason why I'm doing this. Okay, I'll show you. And then I toggle the LED value. Okay, I toggle the LED value each time the IRQ is pressed. Okay, now after I do that, I clear the ISFR bit in the port D register. Okay, so what is the ISFR register? Let's come back here again. Okay, so this ISFR register is a register for each port. It's different from PCR. PCR is a register for each pin. Okay, so every pin has its own individual PCR register. Every port has a standard ISFR register, and that is the interrupt status flag register. Okay, that means when an interrupt is triggered, okay, you can see the definition here. When it is a 1 means the interrupt is detected. Okay, interrupt is detected. Okay, the flag, if the pin is, okay, the flag will remain set until a logic 1 is returned to the flag. Okay, which means what? That means when I read this register, okay, I rightfully would detect that in this case port D pin 6 would be set to a 1. Okay, so it means over here, okay, for the ISFR, for port D, ISFR is 32 bits. Okay, 0, 1 all the way to 31. And if I come into this IRQ handler, it means that 2, 3. Okay, it means that this bit 6 has been set to 1. Correct? This original setting of 1 is because of the hardware. Okay, that means when the interrupt is detected, okay, and the processor is registering this interrupt, it will automatically set this bit for me. Okay, that means it is telling the processor that port D pin 6 has triggered the interrupt. Okay, so that is why this particular bit in ISFR register will be set to a 1. Okay, and as long as this bit is 1, the interrupt is considered to be still to be serviced. So the only way I can tell the NVIC that I have completed the interrupt is I must clear this bit. Okay, I must clear this bit. That means this 1 must become a 0. Okay, this 1 must become a 0, correct? Okay, the 1 must become a 0, then only I have cleared the interrupt, I have serviced the interrupt. But in order for me to clear the bit, okay, what does it say here? It must say until a logic 1 is returned to it. Okay, so in some cases the microcontroller has this kind of things. To clear it, I must write a 1 to it. It's not write a 0 to it, I must write a 1 to it to clear it. So originally it is 1, but I must write a 1 again, then only becomes 0. Okay, so that is why over here, okay, I do a OR operation. Alright, so when I do an OR operation, what am I doing? I'm actually writing a 1 to it. I'm writing a 1 to it so that it becomes 0. Okay, that is how the register is designed. Okay, you write a 1 to it to actually clear the bit. Okay, once I clear the bit, then I will no longer be coming back to this interrupt until the next time it is triggered. Okay, so that is how the whole thing is. So we need to do two things. One is configure the interrupt correctly, and subsequently the IRQ handler. Okay, so what do I do here? okay, this is not again exactly your lab code. I just keep toggling the LED control bit, and in this case, I check whenever the LED control is set to a 1, then I toggle my LED. So I keep toggling between on and off. Okay, if the LED control is 0, then I off the RGB LED. Okay, so that is basically what I do in this demo code over here. Okay, so let me just okay, so the camera is not working today, so I will just have to show like this. Okay, tomorrow I'll try, next time I'll bring a webcam. Okay, so the switch connection, if later on you can come and see, is the same as what is in the picture. So it's only the port D, pin 6 and ground. Okay, now if I, let me download the code first, and then we see what happens. Okay, so if you look at the variables over here, okay, so LED control is originally 1 and the count is 0, correct? Initial count is 0. Now if I run the code, okay, the LED is blinking, correct? The LED is blinking and the count is 0. Now when I press, okay, the LED control has become 0. LED control has become 0. Okay, but the count has become 23, correct? From 0 become 23, which means what? There were 23 transitions that happened. Okay, that's the number of times that the mechanical bounce actually triggered this interrupt. Okay, so this to show you the bounce effect. All right, so the bounce effect, again, how I just hack around is just put a delay first. Okay, so when I first register the interrupt and I do the toggle, I come back to the main loop, correct? And then I just delay myself some random value until I come out of it. So again, this is not an ideal solution, okay, but it's an easy hack just to get past the mechanical bounce. Alright, then if I toggle again, okay, so if I press again you will see that in this case the LED is still off, correct? That means it bounced, and then by the time the delay finished, actually it captured another trigger, so it still remain off. Okay, so now it captured again, so you're now switching. Alright, so basically what you're seeing is that the LED control is toggling while the count is jumping a lot. Alright, again the jump a lot is because I increment my count every time I trigger the IRQ. Okay, now let me just show you this. If I do not clear the status register flag, okay, if I do not clear this, okay, if I do not clear this, then what happens? Okay, so if I do not clear this and I press the switch, okay, you can see that I am forever stuck in the interrupt. Okay, how you know I'm stuck in interrupt? Because the count is keep on increasing. Correct? That means I am perpetually stuck in the interrupt because I do not clear the status flag. So if I do not clear the status flag, okay, what happens is the controller, the NVIC is not updated that the interrupt has been serviced. Okay, so I'm perpetually still servicing the same interrupt again and again and again. So I must clear the status flag so the NVIC does not keep updating me that the interrupt has not been serviced. Okay, so that is why this is important. Okay, so that is basically the the gist of how you're supposed to go about writing the code, okay, for the next week's lab. Okay, so of course you can try it out on your own before the lab as well. The switch would probably be in the lab by tomorrow. Okay, so this one other thing that I want to show you is this. So I just want to capture the debouncing so you see what I'm talking about. Okay, so this is one idea of how the debouncing actually looks like. Okay, so I use the scope on the switch. So you can see that actually there are many triggers. Many triggers which causes this, or which is a normal thing in a mechanical switch. Alright, so that is why we need to be able to handle the debounce in a way that you do not get affected by it. Okay, so what are the other ways you can handle debounce? You can temporarily disable the port D interrupt after I service it the first time, correct? If it's the first time I go to the IRQ handler, means the switch has already been pressed. Okay, then I temporarily disable it first, wait for a while and then re-enable. Okay, if you want a hardware solution, what is the hardware solution? You can put some capacitor there. Why? A capacitor will take time to charge up, correct? Okay, so after the first transition, the second transition, it will charge up slowly. Okay, and by the time you don't have any force trigger already. Okay, so you can approach it in a hardware solution or a software solution approach, depending on what you think sort of works for you. Okay, so there are of course many ways of solving it, which you can experiment. Okay, so that's about it. Okay, so we can now have the Kahoot. I have Arduino Unos to give away. Okay, so give me a while while I set up. Okay, so three Unos. Last semester I only gave the first person. This semester upgrade. All three. Okay, anybody else? Okay, so let's start. Okay, port D. So which bit am I setting here? Bit what? Bit 13, correct? Bit 13 for ICGC5. So let me just check. ICGC5 bit 13, sorry. Bit 12, sorry, bit 12. I'm setting bit 12, which is port D. Okay, bit 12 here, port D. Okay, so we are setting bit 12 to 1. Okay, so that's why you enable power to port D. Okay, so PCR register we just saw. Okay, PCR register okay, it is used for quite a lot of things, correct? IRQ setting, mark setting, okay, pull up, enable, and so on. Okay, so it is a register that you can use for a few different settings. Okay, so only got 3 more questions left, only 5 questions total. Okay, so GPIO, timer, ADC, all these are your peripherals, correct? And all peripherals have a ability to configure your priority using the IPR registers. Okay, so the only thing that maybe you're not familiar is NMI, but NMI actually we have discussed before EPP2. NMI stands for what? Non-maskable interrupt. Okay, non-maskable interrupt is again in the similar category as your reset. That means when it happens, you must entertain the interrupt. You must service the interrupt. You cannot ignore it. All your peripheral interrupts you can choose to ignore. You can clear the interrupt and say I don't want to service. Okay, but a core interrupt, okay, like an NMI or a reset, you cannot ignore. You have to service the interrupt. Okay, all of these core interrupts have a fixed priority level. Okay, C0 means what? Is 1100, correct? C is 1100. 11 is 3, correct? Okay, so 1, 1 is 3 means you are setting the priority of IPR or IRQ 0 to 3. Okay, you have to remember for the IPR registers, okay, we are only configuring the upper 2 bits, correct? Okay, for each of the 8-bit blocks. Okay, so even if you do not know it's IRQ 0, you just look at the upper 2 bits is 1, 1, correct? Of this 8-bit value, so it is a value of 3. Okay, last question. That's why I say you must always have your data sheet standby. Okay, 0x9. Okay, for IRQ, 0x9 means, okay, 9 is 1001, correct? Which is interrupt on rising edge. Okay, so as long as you know how to refer to your data sheet, okay, then I think all of this you should be able to answer. Okay, YZ, SX and ChatGPT. Where you are? Please come down. You are the one, how do you know? Okay, so thank you. So if you have any questions, you can stay back and ask me. Okay, if not, that's all, and I'll see you all next week. Congratulations.